a little talk about the Arctic. So what I study mainly is the Arctic marine system. So that's where I'm going to put most of the emphasis on. That's why the title is Snow-Covered Sea Ice. And I also link it to marine mammals. So my research really looks at the coupling between the physical system and the uh, habitat of large marine mammals, whales, seals, and bears. So that's what I'm going to talk a little bit about today. So next slide, please. Oh, what am I going to talk about? A couple of things. I'm going to talk a little bit about the uniqueness of the Arctic. Why? How is it different than even the southern pole or the Antarctic region? And then I'm going to talk about the importance of snow and ice, why it's important, why we study it. We have a whole research center here at the University of Manitoba that's does a lot of work on snow and sea ice on the marine system. So I'll talk a little bit about that, and then I'm going to look a little bit at my current research. So what that biogeophysical coupling is and how what are some of the main areas that I'm focused on in terms of snow, sea ice, and marine mammals. So the next one, I think there's a yeah. So I'm always asked. This is probably the thing I'm most asked when I go out and tell people what I do is who cares? Why, people when I tell them I study snow on sea ice, their eyes glaze over. They're like, okay, you live in Winnipeg. There's a lot of snow. Why do you go up north? But it's really central to what's happening in the world. There's this interaction between the Arctic region and snow and sea ice being a major component of that, and what we see down south in terms of weather, in terms of our biology, things like that. So everything is coupled together in our Earth system, as probably everybody knows. And the Arctic really plays a major role in that coupling of that connection between the middle latitudes where we live and the higher latitudes. So I'll talk a little bit about that as well and try to get at that question of who cares and why we should study this. So next slide, please. So we'll start with the uniqueness of the Arctic. Why is it unique? So next slide. First is the geography. If you think about the Arctic system and the Arctic from just looking down below, it's really an ocean that's surrounded by land. No real area in the world. This is how we focus on it. There's nothing like this in the world. So there's land, there's the ocean, and then there's pathways to move water in and out of that. So when you think about the Arctic, we're really focused on that marine system. It plays a dominant role in the Arctic. The next slide. So the people, when you think about the Arctic and even compare it to the Antarctic, it's completely different. We have populations in the Arctic that have a certain density depending on the region. There could be a lot of people living in the Arctic. In the Canadian Arctic, it's not so much. In the Eurasian side, there's much more. And the population is also varies in terms of its composition, whether it's in Greenland, where it's mostly the indigenous population, or in parts of Russia and Northern Europe, where it's mostly non-indigenous. And that will affect how we do research. It also affects how we study it. It affects issues like social development and governance. Greenland has its own government based on its indigenous culture, where Canada doesn't. Russia for sure doesn't. And that part of that is due to the fact that there's not a lot of indigenous population in Russia compared to Greenland. And then there's the traditional activities. A lot of what we study and why we study it is because of traditional activities. Snow on sea ice is an integral part of not only my research, but also the Inuits' way of life. So in the Canadian Arctic. So therefore, it plays a pivotal role in what they do, and changes that are happening will significantly impact them even more than what it does for what I study. So next slide. The environment is another way it's unique. It's, again, unlike most other parts in the world, in that it's untouched, and I put that in quotes because it's not really. There's been a lot of industrial activity in certain parts of the Arctic. There still is. But it's relatively unique in the sense that you have an area that has 24-hour daylight and darkness, or periods of 24 hours of daylight and darkness, and that really controls the system itself. and you have snow, you have ice, you have different unique biological communities, and I'll talk about that in a minute. But it's really this idea that it's unlike anywhere in the world. If you've never been to the Arctic, the first time I went to the Arctic in 1995, I guess. Um, if you weren't born yet, don't tell me. But it was amazing. It was, I'll remember that till my dying breath, in terms of getting off the plane and just getting onto the field, onto the snow and ice, and just being in an area where very few people have gone before. But there's a lot of threats to the Arctic right now and to the environment. Things like pollution transport. Um, the Arctic doesn't produce a lot of pollution, but because of the atmospheric circulation and things like that, there's a lot of most of the pollution that's produced in the southern or in the lower latitudes or mid latitudes is transported up into the higher latitudes, including the Arctic. So black carbon is a big one right now, where it'll change the environment significantly, but very little, if any, black carbon is produced in the Arctic. So next slide. And then there's the animals. There's the biology of the system. There's very unique animals to this system in terms of the marine and the terrestrial. There's just examples here. There's an Arctic cod. That's that little fish at the top. That's makes up the base of the food web in the Arctic. This is what most things like seals will eat, and then there's a ring seal below it, taken from the field, and of course the iconic polar bear. If you've never seen a polar bear in the real world outside of a zoo, it's a very unnerving thing. It's the only animal that will stalk a human. I've been stalked many a times, and it's very uncomfortable being a human and being stalked. And I also came between a mother and cub by accident, which was not a smart thing to do. But I digress. I have a lot of polar bear stories. So there's all these animals, and they all work together. It's a very delicate, but not a simple food web. Most people think that it's simple in terms of there's one type of fish, and there might be a couple of species eating those fish, and then a couple of species eating those. It's much more complicated than we thought, but it is very delicate. You start changing one part of that food web. So you change a seal, for instance, that's going to affect a polar bear. It'll affect the fish below it, that which will affect the phytoplankton and zooplankton. So the whole system is changed, unlike in some of the middle latitudes and lower latitudes where it's not as delicate, in the sense that if there is a shift in one species, the other parts of the food web will adjust to it. And with all of these things, and a lot of what I'm going to talk about as we go through this, is the fact that there are a lot of questions that still need to be answered. We don't know. We don't have a complete grasp of where polar bears go, which is what I did for my PhD, looking at their habitat. We don't know what seals do and what their habitats are necessarily, and how they changed over time. If we can't understand the current, it's very difficult to understand what's going to happen in the future. So when we think about that biological physical coupling, or even just the biology of the system, there's a lot of unanswered questions, and things that we're still learning every day in terms of the Arctic food web. Next slide. And then it's change. I don't think I have to tell this audience that the Arctic is undergoing significant change. It's really the bellwether of the Arctic, or of the Earth system. What's happening in the Arctic will probably happen globally, and it's just happening there first and fast. So most of the climate change, the figure on your left there is showing the temperature change between 1960 and 2019. The darker the red, the more temperature change. So you can see most of the Arctic is in a deep red or deeper red, signifying most changes happening up there in that region. And this is just an average over that period. It's not looking at any specific year. If we get into future predictions, that just gets deeper red. So we're projecting that it's going to change even further. And that has consequences on for instance, sea ice concentration. The map on your right is showing the change in sea ice that's happened over this was for September 2012, which is one of the lowest sea ice years on record. The reds, again, just indicate significant change. Blue or a reduction. The blue indicates a increase in sea ice amounts. And what you see is that it's mostly red and darker red, again, showing a large reduction in sea ice. And it's not from across the Arctic. It's really happening in the Western Canadian Arctic, the Beaufort Sea, and then in the Eurasian side of the Arctic. And that has to do with the fact that the ocean circulation pushes the ice up against the Canadian high Arctic, so the archipelago. And you see that'll be the last areas that have ice because of ocean circulation. Now, there's always going to be sea ice in the Arctic, unless the Earth stops tilting on its axis. And we're always going to have a winter period where it's colder, and therefore we're always going to form sea ice. What's happening is that the timing of sea ice is changing. So when it freezes and breaks up, and I'll talk a little bit about that in terms of my research. And then it also affects the type of sea ice. So, 20 years ago when I started my research, now almost 30 years ago, I have to change that mentality. I started very, very young. It was mostly multi-year sea ice that survived one summer, didn't melt completely. Now it's changed to a first-year sea ice dominated regime, which means that the sea ice is melting in the summer. Most of the sea ice is melting in the summer, and then the new ice is forming, which changes everything. From a polar bear perspective, which is what I study, that's good because polar bears like first-year sea ice and seals. But when you talk about what polar bears are going to do in the winter, if there's no sea ice, or in the summer when there's no sea ice, they have to go on land, and they don't eat very much on land. They don't get a lot of energy from food on land. So it's going to create a lot of problems that we still, and again, this gets back to that idea of questions. We still don't know what impact it's going to have. Even talking to polar bear biologists, I'll talk to one about what they think and another one, and they'll give me two different answers because we just don't know what's going to happen. And our models and our projections haven't really been shown to be accurate. So again, it's this idea of we don't know what's going to happen. In one area, we can't really predict what's going to happen in another. So that's why it's unique. It's a very different area to study. It's a very different area to go to and to live in for any amount of time because of these different factors. So next slide. I think it's... So now I want to focus a little bit about the importance of snow and ice and really get to that question of who cares. One of my goals in my life before I die is that people will understand the importance of snow and sea ice. I do it one class at a time, so I have to live to be 1,000 years old, but I'm going to do it. One day, everybody's going to understand this and get an appreciation for snow, at least. So next slide. Snow controls our climate. This is something that I talk about every class I teach from first year to fourth year. I give this slide to every talk I give to groups like you guys. Our climate, our weather in the middle latitudes is really controlled by what happens in the Arctic. And that has to do with two things. One is the ice albedo feedback, or what we call the ice albedo feedback. If you have a lighter surface, like snow and sea ice, it's going to reflect more of the solar energy. If you have a darker surface, like the Arctic Ocean, without the sea ice on it, you're going to have absorbing more sunlight. So the Arctic sea ice, and I learned this term from Polar Bear International. I won't take it as my own, but the Arctic is the Earth's air conditioning. That's what they call it, because it keeps our planet, because of the fact that there is this large time period throughout the year where there's a white surface, it keeps our temperatures cooler. Without even thinking about climate change and what we're doing to our atmosphere, just the fact that we have an area that's covered by snow and ice, reflecting most of the incoming solar radiation, especially in the shoulder seasons in the spring and autumn, that helps to keep our planet, not just the area regionally, but the whole entire planet cooler. Now, if you start adding climate change and you start playing around with our atmosphere. Removing that now, it's just going to help to create a positive feedback. So the ice albedo feedback is a positive feedback and is going to help to reinforce any climate change that we're doing based on greenhouse gases. The other thing is weather patterns. The other impact it has, there is that interconnection between the high latitudes and the middle latitudes. So we'll see a lot of our weather systems are derived from what's going on in the Arctic. There's a lot of work being done on something called teleconnection. And that's this idea that what happens in one area will affect the weather in another area, and it goes both ways. So the Arctic will affect our middle latitude climate, and our middle latitude climate, to some extent, will affect our high latitude climates. When I was an undergrad, that idea of teleconnections never came up. The idea that the Arctic was a region and the weather of that region was based on the properties of that region, only that region. Now, in the last, I would say the last 10 years, we've really come to understand that there is that teleconnection between the two regions. So what happens in one happens in another. And again, it's still a big question on how that works and how what impact it has on, and also how it changes throughout a given year. So next slide. So there's the importance for climate, but there's also the biology. As I alluded to before, the Arctic is not it's a delicate food web system, but it's not simple. And there's a lot of things that live in and on this snow and sea ice. So we have little things like that little organism in the snow and ice that's shown in the one slide with the finger, or in the one photo with the finger. There's a lot of things living in our snow and sea ice, from things like bacteria and viruses to phytoplankton and zooplankton to large animals. Ring seals use the snow and sea ice to create their layers for birthing. They use it for to make holes, breathing holes, things like that. They'll use it as a platform to bask in the summer. It's amazing watching a ring seal who have very poor eyesight lie on sea ice and seeing a bear come up to it and try to get it for a food source. And then it's also, from a polar bear perspective, they use it for all of life's activities. So to feed, to mate, to rear their young, everything. When they go on land, they really don't do much. They're not a terrestrial animal. The other important thing is that it also, so it works as a positive for seals and bears, but from a whale perspective, it's a hindrance. So if there's a heavy ice year, you can get entrapments of whales, which could lead to high mortalities. You can have whales that will come into their traditional feeding areas later because they need the ice to break up. So therefore, they won't be feeding as long, which can create biological issues, things like that. So it can work both ways. It just depends on the species. So beluga whale, for instance, doesn't thrive in ice-covered waters. It really waits till the ice recedes. So if breakup happens later, it could be a problem for beluga whales. If it happens earlier, it might be to their benefit. So it's not all bad, I guess, is what I'm trying to say. From a biological perspective, it's really species-driven in the Arctic. Next slide. And then there's changes, right? And I alluded to this before. Sea ice has significantly changed over the last 30 years. We have records, satellite records going back to the late 1970s, early 1980s. And since then, we've seen a dramatic reduction in sea ice. So what's shown in the middle, or in the figure on the left, is this 2019 summer minimum. So this is the lowest sea ice concentration during the year. And what it was actually one of the lowest on records. There was only 1 or 2 years that it was lower than 2019. And you can see in the yellow line there, that's the median extent for a period from 2018 to, I think it's 2010. And you can see how much it's reduced. And again, most of that reduction is in the Western Canadian Arctic and along the Eurasian coast because of, again, the ocean currents are pushing the ice up against the Canadian Arctic. 2020, and we don't have a complete record yet, but 2020 was one of the lowest. The lines at the bottom there are just the different colors represent the different decades. And you can see the darker lines are lowest. The red line or pink or purple line there is the line for 2019. And you can see it's on the low end, but 2020 is actually lower. I was looking at a record just the other day of that, and the line was actually lower than what we saw there. So much earlier breakup, less concentration in 2020. It's, the pattern is continuing. There's some discussion about, the fact that COVID-19 happened and all the negative for that, but there might be some positive in terms of the impact it'll have on the Arctic system because of, we're not driving as much, we're not creating as much greenhouse gases, so there might be a little bit of a rebound, but there's going to be a lag. So the longer the COVID lasts, maybe the better off it'll be for Arctic and sea ice in rebounding from these very low amounts. The other thing to mention is that it's not just a single year that it's occurring in the Arctic. Most years in the 2010s have been some of the lowest on record. So it's not, some people will argue, well, 2019 may have been just an anomalous year. And what about the other years? Well, 2018 was low, 2017 was low, 2016 was low. Most of the 2010s were low or in that low part of the trend in the data. The graph on the right there is showing snow in the northern hemisphere, and then for January. And snow is something we don't know a lot about. Sea ice, there's still big questions. We know even less about snow. There's two people in Canada that study snow. One of them does terrestrial snow, and one of them does Arctic snow work. So there's not a lot of people studying snow on sea ice. And so there's even bigger questions. So we don't know a lot. So why I mentioned that was the diagram or the graph showing the northern hemisphere snow cover extent. That's for land. It's not for sea ice. We don't have a good record of that. But what it's showing on land, and if we assume it's the same for sea ice, it's significantly decreased over the period since 1967. And a lot of that decrease happened in the last decade or so. So you see the negative bars mostly confined to that period since 2005. In January, though, we see a slightly different record. So we're getting a change in the snow cover extent, so how much snow cover there is, but we're also changing the timing of snow cover. Our winter, we're seeing more snow, and that is because we're seeing warmer temperatures. The atmosphere can hold more water vapor, and therefore there's more precipitation. But really, we're seeing the decline happen again in those shoulder seasons. And snow is important because it acts as an insulator. So if it falls if we get snow being deposited in the fall or in the autumn, that's going to help the sea ice to grow because it insulates the sea ice from the warmth of the atmosphere, and therefore it'll grow faster. If it happens later on in January, it can actually cause the sea ice to become thinner because it protects it from the colder atmosphere. So it could have again, timing is important for snowfall when it happens in the Arctic. So next slide, please. So what do I study? So I gave you a little background on why the Arctic is important, gave you a little background on why snow and sea ice is important. Now I want to talk a little bit about what I study and why I study it. So again, my research interests focus around this idea of biological physical coupling, linking that snow and sea ice work that I do to a practical, some can argue not practical, but practical application to marine mammals. So next slide, please. So why study it? Well, what I study, there's different ways to look at snow. So why I study snow is when you think about snow and you just look out after a snowfall, there's a lot of variation in the surface. And that variation creates different surface features, like a barcan dune, which is shown on the right there, or the left, sorry, pardon. And that's a typical dune you'd get on a sand dune or in a sand environment. It has those arms that come out at a uh, or it's a semicircular or semi-lunar kind of appearance to it, with these arms that bend out in the opposite direction of the wind. The wind is actually coming towards the bottom of that photo. That's what that arrow indicates. So you get these large; these can be uh, meters wide in terms of their spatial scale. You can also get something called syzygy, shown on the far left or far right photo, and that's these smaller, more irregular, kind of eroded dunes on the surface of the snow or the surface of the ice, and these will have different properties, and they'll affect the environment differently. So when you have a barcan dune, for instance, it's going to affect how much light will penetrate down below, and if you look at just the environment or the photo itself, it's pretty uniform unless you get that barcan dune, and therefore you're going to get a significant increase in snow. Snow's a good insulator. It's going to restrict light penetration, so you have less light directly underneath the dune, but more light around in the thinner areas. When you have sastrugi on the other side, it's not as clear cut. You don't have these. You get a lot more variation in the surface topography, so that's going to affect even more. There's going to be more variation in light penetration. You're going to have different environments for different biological species and things like that. What's shown in the middle is what you typically get over multi-year sea ice. These smooth hills, what we call hummocks. The snow will follow them, and multi-year sea ice is much thicker than first-year sea ice because it survived a summer melt, and therefore it's going to catch snow earlier. Snow is typically much deeper. Some of those mounds of snow or hills of snow can be meters in depth, as opposed to a barcan dune or even sastrugi, which is typically in the Canadian Arctic, about 30 to 50 centimeters. So we can have, I've sampled snow on a multi-year sea ice that was 2 meters thick. In the Antarctic, it can be 5-6 meters thick snow cover. But for the Arctic, multi-year sea ice and snow on it is much more much deeper than it will form on first-year sea ice. So it's not just that there's snow on the ground and it changes the radiative properties and the albedo and things like that, but the features themselves are different and will vary spatially and will vary based on what type of ice is underneath it. Barcan dunes typically form on very smooth ice, not a lot of surface irregularities. Sastrugi you get on ice that has undergone some form of irregularity, so you might get small ridges forming, ice that's diverged and then converged again. If you're dealing with a large ridge, which could be meters in height, you could even have areas where there's absolutely no snow cover on it, which again changes the entire system itself. So next slide, please. So how do we measure snow and ice? And this is where the video was, but it's okay. So when I go out and measure it, I'm, again, one of the only people that measures snow on sea ice in Canada. It's not a thrilling job, but pays the bills, as they say. So the way I do it, it's more than just paying the bills for me, but I go out and I sample. I'm in the field and I sample snow depth. So when I started my master's program in 1994 or 5 was my first year in the field, I used a ruler and I measured, I think it was 475 snow depths per site, and I used a ruler. So I would stick the ruler down, lift it, record the number, move on to the next point, do the same thing. I was 2 years old. I had a great back. It was fine. And then over the years, we've developed systems, or others have developed systems that are automated. So what I'm doing there, that's a photo of me in the field, is I'm using what we call a digital snow probe, and it's amazing. You stick it in, you click a button, and it records the snow depth for you. It made my life so much easier. I can't do as much snow depths because I'm, again, not 20 years old, but um, it automates it. So I have, in a sampling season, I can sample. Um, Depends on the type of ice, but I can sample 3 or 4 sites a day for 3 to 6 months. So there's a large volume of, in each site I would have almost 500 data points. So there's a lot of sea ice or snow on sea ice data that I have access to. The other way we do it is through remote sensing. And if you see at the back of that photo, there's a helicopter, and it kind of has a nose on it. It's an instrument. Um, it looks like a Pinocchio nose, and it flies. We fly it at an altitude of 4 meters above the snow, and we can measure the snow and sea ice depth using that instrument. So basically, now what I do is I'll do a couple of those transects, then I get in the helicopter and we fly around at 4 meters above the surface at 100 knots. So we're flying fast and low. It's almost scary at times. You can imagine a sea ice environment. There's a lot of ridges. Ridges can be up to 10 meters in height above the surface. So we're flying at 4 meters above the ice until we can't anymore, until that ridge is right in front of us. Then we have to go up and over it. But we need to stay as low as possible to keep the footprint quite low. So what I do, and what I did for my PhD, and what I'm continuing on after that now, is trying to link the two together. We have a lot of, I sample at 1 meter intervals in situ, but how can we scale it up to what we get with the helicopter, which is on the order of about 10 meters, and then how do we scale it up even higher to satellite imagery? That's the ultimate goal. So next slide. So we use those two different methods. So this is the ultimate thing that controls what I study, what I do. And this is what I'm going to be focusing on for the rest of my career. I probably have another, 20 years left, if I'm lucky. And that was threw me for a loop when I just said that. But what is it? What do I study? So if we look at, and really it's this biological geophysical coupling is what I call it. And this controls everything that I study. This really everything I study links back to this idea. So how does how does the ice surface roughness influence snow distribution, and what impact does that have on Arctic marine mammals? That's the main crust of everything I do, is trying to get at this. And my ultimate goal at the end of my career is to be able to develop a model that is able to do that. So what am I doing? So if you look at the satellite image there, this is a radar image of the high Arctic. So it's showing the black and the gray are sea ice. The white is land. I don't study the land. I study the sea ice. And you can see the variations in the color or the tone of the gray in the sea ice. And that represents different types of ice. So the darker blacks represent smooth ice. It's microwave imagery. The kind of grayer areas are rubble ice. So ice that has a lot of surface roughness, and there's a lot of variation in the surface roughness. Smooth ice, first year ice will be smooth. And then there's also linear ridge elements. That's those long lines of sea ice that are gray or lighter gray. These all will have different types of snow distribution on it, and that is going to be that's going to really control what type of environment you have for marine mammals. So that's the first thing. Am I able to characterize the ice types based on a satellite image? And once I do that, then the next step, and the next slide, please, that's at a quite large scale. But how do we scale it down? We need to be able to scale it down A pixel size in the satellite image might be 250 meters. For a ring seal, it's irrelevant. For a polar bear, that's just too big pixel size. So can we use an instrument? This is the helicopter I was talking about, and you can see the Pinocchio nose. There's a lot of different terms for that device. Some I can't really talk about, but you can imagine a lot of people have taken photos with that. And this is what we fly, and the data in the middle there is the information we get out of it. So you can see the top line is the roughness features. Then there's a histogram of the snow and ice, and then there's the transect. But can I scale? Can I take something at a very coarse resolution, or too coarse for seals and bears, like the satellite image, integrate it with something at a finer resolution, like the helicopter, and then the next slide, to get the roughness elements. And now, can I apply a snow model? Can I develop a snow model that will look at how the snow varies spatially and temporally? The basic idea here is that if I know what the surface roughness is, can I dump a bunch of snow on it, move it around with the wind, and say this is what the snow distribution will look like? Because snow distribution is really the key when we talk about a habitat for marine mammals in the Arctic. It's not just that there is a certain amount of snow, it's really how that snow is distributed over the surface. Rough ice the snow will be distributed differently than smooth ice, and smooth ice will be different than ridge elements. I've done some model development and model testing with that, and the dark line in that diagram there shows what I've observed or what I've measured, and then the dashed lines are all the model runs I ran. And the first thing that you should notice is that there's very little agreement between the two. So the models need a lot of improvement on that, trying to get at that. And that's kind of what I'm working towards now, is developing a better model for this. And then next slide, please, is how then can I apply that to look at a habitat model? If I know what the roughness is, I know what the snow is going to look like on top of that, can I now do some quantitative estimation of what things like mammal densities are based on telemetry data, based on observations, counts, things like that? And that's, the ultimate goal. If I can say, based on a radar image, this is what this ice looks like, this is what the snow will look like if we know how much snow fell, and then this is where the good habitat would be versus the poor habitat for polar bears, ring seals, things like that. This gets at the question of climate change. We don't know what's going to happen to polar bears in the Arctic in terms of climate change with any certainty. We know they're going to be impacted, we just don't know what that impact will be. So this idea of developing that habitat model will help to address that. So if I could say, it was very bad, ring seals don't like smooth ice. They can't build layers on smooth ice. They like the linear ridge features. But if there's very little ridge features, then that's going to cause a crash in ring seal population, which is going to cause a crash ultimately in polar bear populations. So can I do that? Or can I say there's a lot of ridge features, and therefore there's going to be good marine mammal density? So that's how I look at coupling the two. So next slide, please. So this is what I was talking about before. The different ice types control snow distribution. This is a little grainy because this comes from, again, my master's, which was done in the 90s. Computing wasn't as good as it is now. But these are what this is a statistical technique that I use to model the snow distribution. The one on the left is for first-year sea ice. The one on the right is for multi-year sea ice. They're different. First-year sea ice has those nice dunes that are evenly spaced. Multi-year doesn't really have dunes that are evenly spaced. The surface is more irregular in terms of its snow and snow distribution, which again is controlled by what this ice distribution looks like. Next. And then if I take those, I'm able to model what the snow depth is. So this gets at that idea of snow modeling. And what's being shown on the slide now is just a surface created by those features, by those models in the figures below it. I've applied one of the directional variograms there, and I statistically modeled or statistically created an artificial snow cover, and I was able to do that with pretty good accuracy and reliability. But the problem was this is a 100 meter by 100 meter area. So it's not, when you talk about a satellite image that's 250 by 250 meter pixel, this isn't even a single pixel in a satellite image. So kind of how do we scale, how do we control or mitigate those two different scales that we're using and produce a product that's more realistic. This is where I'm kind of moving towards. Next slide, please. So getting into that more of the biological coupling side, I've done work that looks at, for instance, snow distribution and duration and their impacts on ring seal pups. And we've shown that it's really the variation in the spring snow cover, and that's what spring CV is, just the coefficient of variance in the spring snow depth. That and the difference in the snow depth or in the snow cover controls ring seal pups. And when you think about ring seal pups, if they crash one year because there's very little snow depth or variation in snow in the spring, that's going to lead to a crash in Arctic seals, which is going to lead to a crash in polar bears. So these things are intimately linked, and a change in one feature is going to have that impact on. We know that it's going to impact ring seal pups. Polar bears love ring seal pups. They're high in fat. They're also easier to catch, things like that. So they quite enjoy those. Not so much the older ones; they're tougher in all ways, in terms of body composition, in terms of aggressiveness, things like that. So you crash. If there's a crash in the ring seal pups, there will ultimately be a crash in polar bear population for that area. Next slide, please. Work I've done a long time ago that I'm still continuing now is to look at the sea ice changes and their impacts on polar bears. Whenever I talk about what I do, everybody always hears about the polar bear. I don't study polar bears, I study their habitat, so the snow and sea ice. And this is work I started in 1999. I published in 1999, but I've continued on now. And this is for the Western Hudson Bay region, so the Churchill polar bears. And we've seen that in Western Hudson Bay, the graph on the far left is showing the freeze up dates in red and the breakup dates in blue. And what you see is a clear trend. This goes back from 1980 to 2019, is that freeze up is getting later, breakup is getting earlier. So the ice season is getting shorter. Or the difference between those two lines can be seen as the open water season. And you can see as those lines are diverging, the open water season is getting earlier, or is getting longer. So what? Well, the graph in the middle is showing that there's a link between the date of breakup and when the bears are coming on shore. And when I created this graph and did the analysis, me and the polar bear biologist I was working with, Ian Sterling, at the time, we sat there in amazement because there is such a high degree of correlation here. There's about a 2-week period between the date of breakup, which is the line at the bottom, and when the bears are coming ashore. So early, if breakup is getting earlier, bears are coming ashore earlier. And if bears are coming ashore earlier, the next slide, please, their conditions are getting worse. So there's a lot of information on this slide. So or on that graph, I apologize, but all of these things are different conditions of a polar bear. So their natality, their survival of the young, their body condition, so the weight of the polar bear, things like that. And what you see is years where you had an earlier breakup, their condition was worse in the following year because they were coming ashore earlier. They don't eat, and if they do eat, they don't get much nourishment from food on land. So their body conditions are getting lower, And if it's a female and it's coming ashore earlier, a pregnant female, it gives birth, uh, and then the pups have a lower chance of survival. And we see this in Western Hudson Bay. 30 years ago, polar bears were having triplets. That was the norm. And probably most years, three of them, all three or at least two of them would survive. What's happened now is a shift towards twins from triplets. And there's a less of a probability of both surviving. So only one will survive. So we've gone from 3 cubs a year to 1 cub a year in about a 30-year period, which is a significant reduction. I should say now 40-year period. And that's going to, populations stay in that. They're going to be affected. So, and we're seeing that now. There's been a slight increase in polar bear numbers in Churchill. We just don't understand why, because the sea ice, as you can see, is still breaking up earlier and earlier every year and freezing later and later every year. So there's got to be some other. We knew it wasn't as simple as just what happens to sea ice will affect the polar bears, but we know that there's that relationship between the two. So next slide, please. Now, the other part of my research that I've started looking at now is my background is in the Arctic, but also using remote sensing, using satellite imagery and air photos. Is there a way we can count whales from space? So if you ever read something about the beluga population in the Beaufort Sea is X number of whales, they could be. I've seen estimates where it's 20 or 10 to 20,000 whales in the Beaufort Sea. That's a huge difference. That's 100% difference. And the way they estimate that is they do surveys. They fly survey transect lines, and then they have people counting the whales. That costs a lot of money. It costs a lot of time. They can't do it every year. There's a lot of error associated with that. So the idea is, can I take a satellite image or an air photo image like this? And if you kind of squint, you can see those white little dots. Next slide. So if you zoom in, those white little dots there are actually beluga whales. Is there a way to automate the image analysis so I can actually count them? And I've done some preliminary work looking at this. I started this a few years ago, then I had to stop for various reasons. But I was able to get about an 88% accuracy. So I was able to run an algorithm, just put the air photo image in the computer, hit a couple of buttons, run my algorithm, and I was able to count 83% of the whales. Now you see some of the whales are below the surface, some of them are in pods, in groups, so you get some error associated with that. But if I can quantitate that error and say, I know that 30% are below the surface and I'm not counting them, then I can get a much better estimate of whales from space. And this is a big area of research right now, is trying to do this for a number of different whales in a number of different environments. I was going to say, why is this important? Because to do a survey to get an estimate of what the population is can cost hundreds of thousands of dollars by the time you put in people's costs, renting a plane, downtime because the weather isn't good, things like that. And you have a fairly large error associated with that. Or I can order a satellite image for, a satellite image costs me for my study area, it costs me about $5,000 to $10,000 per year. And I can, my time is worth money. So, let's say it's worth 100,000 or 10,000, another $10,000. So I've gone from a couple of $100,000 to a couple of tens of thousands of dollars. It's much cheaper to do it, and I can get a better accuracy using my technique than I can using the aerial photo or aerial surveys. So it's better number. It's cheaper to do. I don't have to hire all these people. There's always logistical issues. There's safety issues with flying in a plane in the Arctic, things like that. I don't need to worry about any of that. So this is the second area. I always like to have multiple research projects going on at the same time. It keeps my head focused, surprisingly. So this is the other area that I'm really interested in, rather than just looking at snow and sea ice. So I think that's it. If I go to the next slide. Oh, right. So I was going to show you a video here of some adaptation to climate change. It's actually a polar bear shaving itself, to show what one potential adaptation to climate change, getting rid of their coat so they can deal with climate change. I always like to show it at the end. It kind of lightens the mood when we talk about climate change in the Arctic, but unfortunately, you can't show it today. So I think that is it, right? So thank you for your time. This is a photo we took flying around. This is obviously a mother and a cub. Uh, we were we weren't chasing it. We were following it. It's not looked on favorably to chase a bear. Um, so we were just following the bear. The pilot never seen a bear before. He was thrilled at that time. We followed it for a couple of minutes and then let it go. So if you have any questions,